All right, hello. Good evening. We are going to do the formal definitions of limit. All right, so last class I covered epsilon, delta. There exists such that, distance, those simple definition. All right, today I'm just going to go straight to the definition. A formal definition of limit. Those of you are math majors, and if you go into higher level of mathematics, that's where you will learn how to prove that. I'm just going to give you the definition of it. If f of x becomes arbitrarily close to a single number, and that number L, as x approaches C from either side, then the limit of f of x as x approaches x approaches C is L, written as limit as x goes to C of f of x equal L. We kind of did one of the problem, right? Let's say limit as x goes to 2 of, let's say, 1 over x plus 2. And in this case, it goes to 4. And this is just a mathematical explanation of what the hell does this mean. So until now, we just did problem like monkey see, monkey do, and if it worked, it worked. But why does it work? So I'm giving a formal definition of it, and this is the one it might super frustrate you guys. And it's also known as epsilon delta definition of limit by Cauchy. Of limit by Cauchy. Let's use this color. Let f be defined this pen is very sharp. Be defined on an open interval containing C and L be a real number. Oh, I didn't add this. On this definition, this means real number. So then limit as x goes to C of f of x equal L. What does it mean mathematically? Means for each epsilon greater than 0, there exists a delta greater than 0 such that if distance from C is greater than 0 but less than delta, then the distance of f of x to L is going to be less than epsilon. Graphically, what that means is, let's say I have this function, something like that. That's C, and I go C plus delta, C minus delta. And f of C equals L, so this point is C and L. It's saying that the distance you get right over here, given L, is going to be n minus epsilon, and this last one would be L plus epsilon. So let me give you English meaning of what the heck is happening. Okay. All right. If you guys don't like certain colors, let me know. If you guys want me to use certain color, please let me know. Okay. If you guys are colorblind to certain color, let me know. I had a student who couldn't see red. All right. So what does it mean in English? Means if we say an error in how far we are from the actual limit, which is epsilon, then there is also an error coming from the x direction. Which is delta. The positive distance between the x value and C has to be larger than 0 but less than delta. If this is true, then the difference between the actual y value of the limit and the y value of the error f of x must be greater than 0 but less than epsilon. So this is a really hard understanding of it, and I truly expect that most of you will not understand what the heck is happening. We're not gonna learn how to prove it, but we're gonna see the application of it. Why, when we take a limit, why certain things are true. So let's look at an example problem. Finding delta for a given epsilon. So this is given limit as x goes to 3 of 2x minus 5 is 1. This is given. Find delta such that 2x minus 5 minus 1, which is less than 0, 1. Whenever x minus c is less than delta. The given part is this right over here. That's your epsilon. So how could, well, if you look at this problem, you look at it, yeah, I mean, when we, like, if I plug it into the limit one, obviously it's going to be 1, all right? 3 times 2, 6 minus 5 is 1. But why are we all these crazy extra things? This is to prove us why mathematically this is true. So let me rewrite it again. In this problem, we are working with a given value epsilon, namely epsilon is 0.01. So to find delta, to find appropriate delta, so let's look at it. 2x minus 5 minus 1. Well, let's simplify it. What happens? You get 2x minus 6, and this looks like x minus 3. What does this look like? Doesn't that look like this x minus c we have right over here? And c is what in this case? C is what? 3, because limit as x goes to 3. That's your c. So right there, we have to start with f of x minus L, make it somehow look like something times x minus c. It's almost like a vector with the scalar, things like that. So we know 2x minus 5 minus 1 is less than 0.01, which is equivalent to 2 times x minus 3 minus 0.01. Boom, right there we can say what? That x minus 3 is less than 0.01 over 2. And we can say that could be our new delta. Well, that is our delta. That is our delta. Here's why. So delta is 0.005, right? So if you say this works, say let delta be 0.005, would that make the statement f of x minus L less than epsilon? Will it work? By using this delta. So let's say 0.0 x minus 3 is say 0.005, And then we're going to reverse work what we did earlier. X minus 3 is technically what does that look like, x minus 3? This is technically what, 2x minus 5 minus 1, right? And that gives us 2 times x minus 3, which is still less than, we know this is less than 2 times 0.005. Voila. So from there, we know that x minus 3 is, this is actually what, 0.01, which is the epsilon. So now we get f of x minus L is less than epsilon. All right, this is a hard one, and we have to do it remote, and that's why it can get hard. So don't panic. Don't worry about it. I'm not going to give you a lot of questions on it because we're remote. All right, so I'm going to stop this lecture, and I'm going to do evaluating limits analytically.